we need to calculate the length of a water surface profile in a gradually varied flow. So the method that we are going to use is the direct step method. So how to find the length of this profile that we need to find, and the method, simple method that we are going to use is the direct step method. So I'll be just drawing, this is the river bed and water is flowing down, so let this be the water surface. Water is going like this, and your energy surface be at another slope. Since this is non-uniform flow, I don't know how it is varying, just varying. This is a river bed, this is the slope of the water surface, this is the slope of the total energy line. So I'm considering just two sections, section 1 and section 2. So I'm considering two sections here, section 1 and section 2. The time being, this distance, the horizontal distance between this, I'm writing the horizontal distance between these 2 points as dx. If I'm joining this like this horizontal distance, let it be dx. Okay, fine. Now I'm just, for the time being, I can even assume this to be as the datum. It's all up to me. I can assume whatever datum I want to. So I'm assuming this to be the datum. Now the depth of water here, the depth of water in the first section, the depth of water is y1. Similarly, the depth of water in the second section is y2. So you have got y1 and y2. And the velocity head at the first section, let it be v1 square by 2g at the first section. Similarly, at the second section, it is v2 square by 2g. Okay. Now for the time, just I'm drawing this, I'm just drawing horizontal lines here. Just drawing horizontal lines. Now if this is dx, this also will be dx. Undoubtedly this also will be dx. No doubt there. Fine. Now the bed is having a slope S0. Similarly, the slope of this total energy line is SF. The bed is having a slope of S0 and the total energy line is having a slope of SF. So I'm just drawing a small triangle here. Let this angle be theta. Then the slope is given by tan theta, that we know. Tan theta is nothing but the opposite side by adjacent side. So this is the opposite side A. This is the adjacent side, which is B, which is, I can write A by B. Similarly, if I take this triangle, see this triangle. If I take that triangle there, you know the slope there is S0 and this distance is dx. I don't know this side. So how do I find out this side? I can say that the slope is equal to, if I am writing this to be the unknown side, this is the unknown side. So slope is equal to unknown side divided by dx. And slope, you know, it is S0. So slope is equal to S0 and the unknown side by dx. So the unknown side is equal to S0 into dx. It means that this distance is equal to S0 into dx. S0 into dx. So this is the height from the assumed data. That's the height. Similarly, if I check here, this line is having a slope of SF and this is having a length of dx. That means that this height, or rather this distance, is equal to SF into dx. That is SF into dx. So I've got this S0 into dx and SF into dx. So no issues there. Now I need to write the energy, the total energy between 1 and 2. Total energy is between 1 and 2. I'm assuming that there's no loss. If there's no loss for an ideal fluid, the total energy at first section has to be equal to total energy at the second section. That I hope you remember. This total energy at section 1 should be equal to total energy at section 2. This is the datum. So first I need to find the height of this above the datum. The height of it above the datum. So it means that it's equal to, okay, fine. So the total energy at first section should be equal to total energy at the second section. Here what happens is the total energy at the first section. So first is the datum head. Datum head is S0 into dx plus then the pressure head y1 plus the velocity head V1 square by 2G. So that's the equation up to here. This has to be equal to total energy at second section. The datum is coinciding. If the datum is 0, then you have Y2 plus the velocity at V2 square by 2G. That is just the energy if there was no losses, but you have a loss here, so that's why the total energy is coming down. So here the loss due to the friction is SF into dx plus SF into dx. So this equation is for a real fluid, as I said. For it was, if it was an ideal fluid, there won't be any change in the total energy line. It would have been straight line. But here the total energy line is going down. It means this is the losses. So total energy at the first is equal to total energy at the second section. And when you consider total energy at the second section, you have to consider this head losses also. So S0 dx plus y1 into v1 square by 2g plus y2 is equal to y2 plus v2 square by 2g plus sf into dx. This is the equation you get. S0 dx plus y1 plus v1 square by 2g is equal to sf dx plus v2 square by 2g plus y2. Now the total energy, we have seen that total energy. Now if you see at the first section, what is the specific energy? We have seen that specific energy is when we assume that the datum is coinciding with the bed level. So when you consider the specific energy at the first section, it will be y1 plus v1 square by 2g. Similarly, the specific energy at the second section will be y2 plus v2 square by 2g. That is, the specific energy at the first section, E1, is equal to v1 square by 2g plus y1. And similarly, the specific energy at the second section is equal to v2 square by 2g plus y2. And just substitute here y1 plus v1 square. Here this is E2, this is E1. And if you substitute that, you can write S0 dx plus E1 is equal to SF dx plus E2. This equation will be getting. Now I'll be taking the energy terms together and this S0 dx terms together. So I can write S0 dx minus SF dx is equal to E2 minus E1 E2 minus E1. In both terms you have dx. So dx is equal to S0 minus SF, which is equal to E2 minus E1. So I can write dx is equal to E2 minus E1 by S0 minus SF. So this is the equation which we need. Or rather, this can be written as the dx is equal to change in energy delta E by S0 minus SF. This is a general equation, and this is the equation through which we have to integrate this equation so as to get the value of the length of the water profile. And right now you might be thinking, what is this length of the water profile? See, we have seen that if you have got an M1 profile, it will be something like this. If you have NDL like this, NDL, you have CDL like this, this is the riverbed. So if you have got something like this, the M1 profile will be something like this. I need to calculate this length of this from here to here. That's the length of the M1 profile. So I need to calculate the length from here to here, and for that this equation is being used. So this is the method. We'll be discussing more about the method in the class, but this is how we'll be this equation we have to use. So changing energy by S0 minus SF is the equation to find the length of the water surface profile. And similarly for M2 profile, it meets NDL at parallelly, and it will be meeting CDL at 90 degrees. So it will be going like this. I need to find this length, the length from here to here, that is the M2 profile. So we need to calculate the length. There also we'll be using this equation. Similarly for M3 profile, it will be meeting CDL at 90 degree and it will be moving like this. So here also for M3 profile, whatever be the profile, we need to calculate the length from starting to the end. We need to calculate the length. For that we'll be using this equation.